All right, today we're going to break down a problem that's a total classic in coding interviews. Seriously, you see this one all the time. It's all about merging a bunch of sorted lists, and it's a huge deal for efficient data processing. We're going to see how a really simple analogy can help us totally master a super powerful algorithm. So, picture this. You've got hundreds of live data feeds streaming in. Think stock tickers, sensor data, you name it. Each one is already sorted. Now your job is to combine them all into one single, massive, perfectly sorted stream, and you have to do it without your system completely grinding to a halt. That's the core challenge we're tackling today. Okay, let's get a bit more formal and really define the problem we're about to solve. So the goal sounds pretty simple, right? You're given K separate, sorted lists, and you just need to merge them into one big sorted list. The two letters you gotta remember here are K, that's how many lists you have, and N, which is the total number of elements across all the lists put together. Trust me, these two are gonna be super important when we start talking about speed and efficiency. Now, before we get all technical and start throwing around data structures and code, let's build a mental model first. An analogy that makes this whole thing just click. Okay, so just imagine you're standing in front of K conveyor belts. Each belt has a line of items on it, let's say numbers, and they're already sorted smallest to largest. The very smallest number on each belt is sitting right there at the front, just waiting for you. The method here is just beautifully simple. Step 1, you glance at the item at the front of every single belt. Step 2, you just pick the smallest one out of that little group. Step 3, you grab that smallest item and you add it to your final merged list. And then step 4, the belt you just picked from, it automatically scoots its next item to the front. And you just repeat over and over until all those belts are totally empty. Simple, right? So that conveyor belt idea is awesome, but there's a catch. What's the magic that lets us instantly find the smallest item every single time? How do we build that? Well, for that, we need a special tool from our computer science toolbox, a data structure that's literally built for this exact job. And this is where it all connects. It's actually pretty cool how perfectly our analogy maps to the real algorithm. The K conveyor belts, those are our K sorted linked lists. The item at the front of each belt, that's just the head node of each list, and that magic basket that always knows the smallest item. In the world of algorithms, we call that a min heap, and the act of picking the smallest, that's just a simple heat pop operation. See? A perfect one-to-one match. So what exactly is a min heap? Well, the easiest way to think about it is like a special kind of basket. No matter what you throw in, it's built to do one thing incredibly well: instantly give you the smallest item. It's often called a priority queue, which is a great name, right? It always knows which item has the highest priority, which for us just means the smallest value. All right, here's the algorithm in action. Step 1, we kick things off. We take the very first node from each of our K lists and we toss them into our min heap. Step 2, we start a loop that keeps going as long as there's anything in the heap. Inside that loop, we do a few things. First, we pop the smallest node from the heap. That's our magic basket handing us the next item for our final list. Then, we append that node to our result. And here's the key part. We advance. If the node we just popped has a next buddy in its original list, we push that next node right into the heap. We just keep this cycle going, pop, append, push, until the heap is empty, and we're done. Okay, quick interview pro tip, especially if you're coding this in Python. You might run into a tricky little bug. If two nodes have the exact same value, the heap can get confused and try to compare the node objects themselves, which usually throws an error. The slick way to fix this is to push a tuple onto the heap. You push the value first, then a unique tiebreaker, like a simple counter, and then the node object. This way, the heap has a clear, reliable way to sort things, even when the values are tied. So, great, we've got a working algorithm. But the big question in any interview is it any good? Is it fast? Is it efficient? Let's dive into the performance. The time complexity comes out to O(n) log k. So what does that actually mean? Well, the n is pretty straightforward. We have to touch every single element at least once, and there are n total elements. The log k part, now that's the real magic of the heap. It means that the cost of finding the smallest item grows incredibly slowly. So even if you go from, say, 10 lists to 100 lists, the time it takes to find the minimum doesn't explode. It barely budges. That log k is what makes this whole thing so crazy efficient when you're dealing with a lot of lists. And memory usage, even better. The space complexity is just okay. This is absolutely fantastic. It means the extra memory we need depends only on the number of lists, k, not the grand total of elements, n. At any given moment, our heap will only ever hold, at most, k items, one from each conveyor belt, right? So it's super memory efficient.
So, how does our heap solution stack up against other ways of doing this? Well, as you can see, it's right up there at the top. It's considered optimal, sitting right next to another great approach called divide and conquer. But here's the one you really need to watch out for, the common trap: sequential merging. Just merging list 1 into list 2, then that result into list 3, and so on. It feels simple, but its performance is awful. O of k times n. If k is large, that's the difference between a solution that finishes in a second and one that just times out.
So why does all this matter? I mean, why did we go through this whole deep dive? Because knowing this stuff inside and out is exactly what separates a good interview answer from a great one. Think of this as your interview cheat sheet. Here's how you nail the answer. First, clearly define your variables n and k. Then, confidently state the optimal time and space complexities. O of n log k time, O of k space. Make sure to mention that both the heap and divide and conquer methods are optimal solutions. Then, show your depth of knowledge by contrasting this with the slow, naive O of kn approach. And, for bonus points, absolutely explain that Python tuple trick for handling ties, and don't forget to talk about edge cases. Like what if you get 0 lists, or just 1, or maybe some of them are empty.
And there you have it, the elegant, super efficient heap solution. The big takeaway is just how powerful that min heap is, letting us instantly grab the next smallest element from a group of k lists. Now, we saw that divide and conquer has the same great time complexity, O(n) log k. So that leaves us with a final, interesting question. If they're both optimal, could one still be better than the other in certain situations? What do you think? Maybe consider things like the memory overhead from recursion versus the straightforward iterative loop of the heap. That's the kind of thinking that takes you from just knowing an answer to really, truly understanding the trade-offs.